So up till now, all of the examples we've been using pure compounds. But if you go into a chemistry lab and you look at the chemical cabinet, there's very few pure compounds, pure elements. You're going to have mixtures most of the time. Okay? So remember, mixtures are samples that contain two or more substances that physically combine, they react chemically, and like I said, they're very, very common. And the composition of the mixture is going to be very important to determine the properties of that mixture. A particular type of mixture is a solution. A solution is another term for a homogeneous mixture. Remember, it's a mixture in which you cannot tell the different components, like when you dissolve sugar in water, you cannot see the sugar. Okay? How much of every compound you have in a solution? That's the concentration. And there's two components, at least two components in a solution. You have the solvent. That's the one that you have the most of, the one that you dissolve everything else into, like you're making sweet tea. Well, the major component of your sweet tea is water. That's the solvent. The solute is the one that you have least of, there may be more than one, and you dissolve it into the solvent. So back to your sweet tea, you're going to have the components from the tea, you're going to have sugar, all of those are solutes. And anytime you have a solution in water, we call that an aqueous solution. And that's a term we're going to be using all the time, so be familiar with it. The most common way of measuring concentration in chemistry is molarity, and it's represented with an uppercase M, and please uppercase, okay? You see in a minute why. But most chemists use molarity because molarity is the number of moles of solute in 1 liter of solution. So since we're always dealing with moles, remember the previous video? What did we do with the grams? Change them to moles. So we're going to be dealing with moles, okay? That's very useful because if you know the volume, you can calculate how many moles you have. So this formula you need to know, but really it's just a definition. I usually give my students many formulas, but whenever the formula is a definition, I don't. You need to know that, okay? So for instance, you have a soft drink. The volume is 355 milliliters, and it tells you has 0.133 moles of sugar. So what is the molar concentration of sugar? Well, first thing, remember, is moles per liter. So you have to change the milliliters to liters. So it's moles of solute divided by the liters of solution. The moles of solute are given. I change 350 milliliters to liters. Remember, 1 liter has 1,000 milliliters, so milliliters cancels out. That's the molarity, or moles per liter. Okay. One thing that I always tell you to be very careful: 3 significant figures, 3 significant figures, 3 significant figures. Units, sig figs. So that is the correct answer. By writing it down like this, you can see milliliters cancels out, you have moles per liter, you know that's molarity, so you know you have the units right, you know you have the sig figs right, you know you're right. Don't you love it? Now sometimes you do dilutions. You lower the concentration of a solution by adding more solvent. Okay? That's a very common way of preparing something of desired concentration. If you go to a lab, you don't have every possible solution of every possible concentration of every possible solution. It doesn't make any sense. Like if I need sulfuric acid, I buy a bunch of the stock solution of sulfuric acid that's usually 18 molar. And then if I need 1 molar, I dilute it. If I need 3 molar, I just make the solutions that I need for the lab. Okay? It's really very, very simple to do calculations. This is an example of a dilution. This is copper nitrate, it's blue. The most concentrated one has the lower volume. This has a high concentration. It has a low volume. When you dilute it, that lowers the concentration, but raises the volume. I know it seems like common sense, but I've seen way too many students get this backwards, okay? So can we calculate how much water do I need to add to get to a certain concentration? Or if I know how much water I'm adding, what is the new concentration? Yeah, and it's very easy. You need to keep in mind that the number of moles can be calculated. We say molarity is the number of moles divided by the volume. So if you want to know the number of moles, volume is dividing, so it goes to the other side multiplying. We are going to call 1 and 2 to before or after the dilution. So before the dilution, the number of moles is the initial concentration times the initial volume. After the dilution, the number of moles is going to be the final concentration times the final volume. Keep in mind, when we're doing a dilution, we add solvent. We don't change the amount of solute, right? The number of moles before and after is the same. We only add solvent. So since the number of moles does not change, you can see that the concentration before times the volume before equals the concentration after. And this is kind of problem where they're going to give you have 4 variables, they're going to give you 3 and ask for a 4th one. Most of the time they give you the original and they say, if I want a certain concentration, what volume do I need? If I want to calculate the volume, it's going to be M1 V1 divided by N2. Or if I add a certain amount, what is going to be the new concentration? M1 V1 divided by V2. You can isolate and in there. You don't have to use molarity. You can use other units if you want to, as long as you're consistent and use the same ones on both sides. Okay? So let's look at an example. You have this volume of this concentration of copper nitrate. I'm going to dilute it to this new volume. So what is the new concentration? They're asking you for the new concentration, so we said that's the formula. All you have to do is substitute. What I like to do when I'm doing these problems to make sure I don't make a mistake, because that's the only thing you can do, put the wrong number in the wrong place. I go through this and say, okay, this is my initial volume. This is my initial concentration. This is my final volume. So now I say, okay, M1 is 5 molar. And don't forget all the significant. V1, 0.850. V2, 1.80. So I do the calculation. The smallest number is 3 significant figures, so there you go. You also know layers and layers cancel out, so the unit is right too. The only problem I had with the students here is when they reverse the volumes. Okay? That's why I said take the time to write down this is first volume, this is first concentration, this second volume, because then you're sure that you put the right number in the right place. But at the same time, you can use common sense. If you reverse the volumes, you're going to get a concentration that's higher. 1.8 divided by 0.8, that's more than 1. So you come up with a higher concentration. If you're diluting, you should get a lower concentration. And sometimes I tell students, before you do the numbers, should the concentration be higher or lower? Oh, it should be low. Because we're diluting. Well, 2.36 is less than 5. So guess what? You're right. You double check. Not only by writing down what this number is, you make sure you put it in the right place, but you can double check. I was expecting a number less than 5. I came up with a number less than 5. And the units cancel out. You have 3 checks that you are right. What could go wrong? Now, there's other units of concentrations. Like I say, molarity is very useful, but we use some other ones. We're going to be talking about mass percentage, volume percentage, mass volume percentage, parts per million, parts per billion. You have molarity that we're not going to talk about it. We'll talk about that in college chemistry too. It's represented with a little case m. That's why I say make sure when you write molarity that you put uppercase. And this is going to be very important when we talk about properties of solutions, like why adding salt to water makes it freeze at a lower temperature, things like that. So we'll do all of that in college chemistry too. Okay? And we're not going to define molarity today. I just mention it because when I don't, then someone comes and says, Oh, when you listed units, you never talk about molarity. Okay. I mentioned it, but we are not going to cover it until next semester. Mass percentage is the ratio of the component's mass to the mass of the solution times 100, because that's percentage in here. Usually, you add so many grams of sugar to so many grams of water, so you're interested in the mass percentage of the solutes, although sometimes in biology, I confuse my students a lot when we talk about osmolarity, talking about the concentration of the solvent. Don't worry about that today. You're not likely to run into problems. But still, even if you do that, let's say that I said you have 3 grams of sugar in 100 grams of water. 100 grams of solution, sorry. If I want to know the percent of sugar, it's going to be 3 divided by 100 times 100, so it's 3%. But if I wanted to know the concentration of water, you say, okay, I have 100 grams of solution, 3 sugar, so 100 minus 3, that's the amount of the water, divided by 100 times 100. That's 97 divided by 100 times 100, so that's 97%. Or you can go the easy way, and you say, okay, if the sugar is 3%, 100% minus 3%, that's 97%. You have to actually go through the calculations. When you're dealing with liquids, you're likely to use volume percentage because you're looking at the volume of the solute. Okay? But the volume of the solute divided by the volume of the solution. You go to the store to buy hydrogen peroxide, and it's 3%. Why? Because you have 3 grams of hydrogen peroxide, which is liquid, in 100 grams of solution. Oh, sorry, 3 milliliters. I'm sorry, I wasn't thinking. Yeah, that's volume percentage, because you're mixing a liquid in a liquid. You could weigh it if you wanted, but most commonly you're going to use volume. Sometimes when you're dissolving a solid in a liquid, you use mass volume, because it's more convenient. You're likely to measure the volume of the liquid, but it's easier to measure the mass. So, like for instance, saline is 0.9%. That means that you have 0.9 grams of sodium chloride in 100 milliliters of solution. It's mass per volume, but it's still percentage. Okay? Now keep in mind, this is very important. Maybe not today, but if you're going to take chemistry 2, solution. Okay? Because you will see cases where we're talking about the solvent only. Just keep in mind, with molarity, we're going to be talking about solvent. Okay? If you know it now, then you don't have to worry when you go to college chemistry 2. Okay? Finally, when you're talking about very small amounts, we use parts per million and parts per billion. The last time I did this in a face-to-face class, I actually downloaded the world report from CPW, and we were reading the components, and there were certain things, like lead, that was in parts per billion. Things that are in very, 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 very small amounts are represented like that. You had a formula, the same mass of solute, mass of solution, in parts per million is times 10 to the 6, in parts per billion times 10 to the 9. I always tell the students, think on percentage as parts percent. Parts percent, doesn't sound familiar? What is that? Mass of the solute divided by mass solution times 100, 10 to the 2. So when you're talking about percentage, it's 10 to the 2. Billion, 10 to the 9. Million, 10 to the 6. But the basic value of the formula is the same. Depending which unit, you multiply times a different number. If you think of percentage as past percent, then you can compare the other ones, and guess what? You don't have to memorize another formula. So if you have questions, if you want to do any of the worksheets, you know what to do. Go to the video description, click on the link to my Wasant account, make an appointment, and I will be glad to share my worksheets with you, answer questions, whatever you want to do.